So what I will be doing today is I will introduce the physics case, what kind of science drives our research, what it is we do, what's the Higgs boson. And in trying to go for these goals and attain these goals, we have to deal with a tremendous amount of technological challenges that once solved create solutions to problems beyond particle physics, being the big data problem and the implementation of artificial intelligence in modeling, one of the spin-offs of this activity. And as such, back in 2020, as the chair correctly pointed out, we started contributing to the modeling of the pandemic using techniques developed at the Large Hadron Collider at the European Laboratory, CERN. All right, so I'm going to start now introducing the physics case. And in order to do that, it's very important to go through this graph where we assign a particular size or distance to a particular type of field in physics. As you can see, when we go to the left, we go to small distances. When we go to the right, we go to large distances. And different types of physics and different fields in physics have a particular size that they study. Nuclear physics stems from atomic physics. When energies of particles increased, you basically look at smaller and smaller distances. So you start resolving the atom and be able to see the nucleus that the atom is composed of. As the energy increases, then we have the emergence of particle physics that looks at the structure of the nucleus and goes much deeper than the size of the nucleus. And as we increase energies, we basically probe smaller and smaller distances. On the other side of the spectrum, you've got astrophysics, you have cosmology, and gradually we go into the exploration of larger and larger distances. So the notion of distance is extremely important to classify what each field in physics does. Now, when you look at this picture, it looks as if the Large Hadron Collider and the SKA do two different things. And the reality and the fact of the matter is that we are actually doing something extremely similar. We are after very similar things. And in order to explain this, it's important to turn this, one-dimensional picture into something that is more like this, where the actual goals in physics, as you go to smaller distances or larger distances, become very, very similar. And one of the key ingredients to that synergy of small distance exploration and large distance exploration, LHC versus SKA, is the origin of mass in the universe. Okay, and I will try to explain how we actually do that by exploring small distances. I don't have time to go through what the SKA does. That has been covered elsewhere. But what is important to us at this point in time is to ensure that we have a strong synergistic connection between particle physics and cosmology, even though we look at things very, very different. And this point and that connection revolves around the origin of mass in the universe. Where does mass come from? All right, so if we look now at the problem of the small frontier, as I said earlier, matter, at least the known matter, is composed of atoms, which have a particular size, as you see basically there, 10 to the minus 10 meters. As the energy of collisions and the energy of the exploration increases, then we are basically able to resolve what's inside the atom. It's already been known for over 100 years that the atom is composed of a very heavy and compact nucleus where electrons are basically orbiting around them, filling a particular set of trajectories. Then as the energy of collisions is enhanced, we basically, particle physics emerges from nuclear physics and becomes a distinct field in physics, in that now we are exploring the substructure of the nucleus by looking at the substructure of its components, being those the proton and the neutron. Now, inside the proton and the neutron, because a proton and neutron, even though it's very small, 10 to the minus 15 meters, is not an elementary particle. It has constituents. Those constituents are known to be the quarks, and which have an even smaller size. And in order to explore them, we need even more and more energy. To date, the quarks are thought as being elementary particles. We so far haven't identified any structure within the quarks. So up until this point, what we call the standard model of physics and the standard model of fundamental interactions, we think of quarks as elementary particles that the protons and neutrons are made of, and the nucleus is made of protons and neutrons, and then the atom is composed of the nucleus and the electrons. In addition to that, we have to take into account forces in nature. So we have matter, we have elementary particles that the matter is composed of, and then these elementary particles interact with each other. And so far, we know that there are 4 types. One type of interactions is gravity, which surprisingly enough is not really a part of the standard model of particle physics, but we know gravity exists, and it has a lot of theoretical development to understand it. Then we have the strong interaction, which is the force that binds protons and neutrons together and is typically related or referred to as a nuclear force. Then we have the very well-known electromagnetism, and another type of force, which is what we call the weak force, which is related to a particular type of nuclear reactions that happen much less often. And in the context of the standard model of physics, of particle physics, the electromagnetism and the weak force are united into what we refer to the electroweak interaction. And this basically leads us to what we refer to as the standard model of particle physics that explains to date what matter is composed of, or at least the known matter in the universe is composed of. In terms of quarks and leptons, these are the building blocks of matter, which are organized according to generations. As we go from left to right, these particles become heavier and heavier. And they are organized in terms of 3 generations of matter. So everything that we know in the universe, as far as the known matter is concerned, and remember, we only know few percent of the matter energy budget in the universe. What we call matter, what we touch and is tangible to us, that we call matter, is only a small fraction of what we have in the universe, is basically explained with this compact system of particles, okay, which are organized in 3 generations. These particles, of course, interact with each other, and they do that through mediators that carry force, being the photon, the carrier of the electromagnetic force. The gluon is the carrier of the strong force, and the W and Z bosons are the carrier of the weak force. And as I said earlier, the electroweak force includes the W, Z, and gamma in a compact way, in a unified way. And this is how quarks and leptons and matter really interacts within itself. The Higgs boson, however, plays a very particular and very well-defined role, distinct from any other particle in the universe, in any other particle in the known matter in the universe, in that the Higgs boson is responsible to provide mass to quarks and leptons, and also the W and the Z boson. It does it with a particular mechanism that was proposed in 1964 by a bunch of theorists, who, after the discovery of the Higgs boson in 2012, got the Nobel Prize in 2013. And the Higgs boson is very important, not just because now we know the mechanism that through which known mass is acquired, but it opens the door to the exploration of the rest of the mass in the universe. This mechanism now opens the door to exploring and trying to understand, what kind of matter do we have out there in the universe, because most of the matter in the universe is unknown to us, and how that matter is generated. So in a sense, to us, for particle physics, our fundamental interactions to discover the Higgs boson in 2012 was the discovery of the century. It's not just a culmination and of the standard model and the victory of it, but on the other hand, opens the door to new discoveries and new explorations. Now we have the Large Hadron Collider. Large Hadron Collider is what we call the energy frontier. As I said earlier, the more energy, the smaller the distances we explore. So you can think of an accelerator as a very powerful microscope. Okay, that's really what an accelerator is. And the Large Hadron Collider at CERN in the Geneva area of Switzerland and also in France became the energy frontier in 2010, and it remains the energy frontier to date, and it will be taking data till the beginning of the 40s. It is basically a system of magnets that keep protons in a circular trajectory, a tunnel which is about 27 kilometers in length, that sits in the boundary between Switzerland and France in the Geneva area. And it contains a number of experiments where those collisions are recorded. You can think of experiments as a very complicated camera that takes data. And this already links up with the biggest challenge of all that the Large Hadron Collider put forward, which is the problem of big data and artificial intelligence. And that will connect later with the problem of COVID. And I will try to connect why a particle physicist is able to deal with complex problems of modeling is because we have to deal with a tremendous amount of data that is produced by the Large Hadron Collider. The South Africa CERN consortium is now fairly large. It's actually now a fairly large community that has grown a lot over the past 10 years, and it contributes to the ALICE, ATLAS, ESOL, the experiments, and it also has a theoretical component. And as of a few weeks ago, it also has a technology transfer component that goes along with it. And I will be talking about it during the second half of my presentation. What we do in particle physics is we take an accelerator. The accelerator injects energy to the particle. The particle, in this case, protons, are accelerated to very, very close to the speed of light, 0.9999% of the speed of light, and then the partons within collide head-on, and as we inject energy, mass is produced. The Higgs decays instantaneously almost. It's a very short-lived particle, about 10 to the minus 25 seconds. That means technically instantaneous decay into something else. So what we detect with sensors and instrumentation is not really the Higgs boson, but the decay products of the decay boson. Okay, and that's one of the reasons. One of the main reasons why the ATLAS detector and other detectors were built, in particular the CMS detector as well, is in order to capture the decay of the Higgs boson among a tremendous amount of other non-interesting data or non-interesting particles in that they have been discovered before, or they are very well understood, and we don't need more research on them. So it's really, the problem is about finding a needle in a haystack. That's really what the challenge of the Large Hadron Collider and the Higgs boson is and was, and the search for new particles continues to be. What you see there is the ATLAS detector at the bottom in blue color, and it sits basically about 100 meters underground, where the protons come from the left and from the right, and they collide at the center of the detector. What you can see there is a schematic representation, a 3D view of a Higgs candidate. You will see later in an animation how we collect data and establish the evidence of a new particle, in this particular case, the Higgs boson. Okay, so what you see there is basically a 3D view of the Atlas detector. The protons come from the right and the left, and they collide. They are tuned, the accelerator physicists tune the beams so that they collide very close to the geometrical center of the detector. And what you see there is that two protons collided, and then two partons within the proton collided head-on, and then a Higgs boson was produced that decayed into 4 muons, muons being the heavier partner of the electron. It's like an electron, but heavier. And you see there, there's, I mean, for a particle physicist, really is a spectacular signature to see these very clean traces of muons coming from one point, and how the detector basically is the evidence for muons going through meters and meters of sensors, and how the whole thing is read out and reconstructed signature. This is a spectacular signature of a Higgs boson. Now, the way, in order for illustration purposes, we basically take out the sensors that don't participate in the detection, but in principle, the detector is hermetic and has full azimuthal angle coverage and great polar angle coverage as well. So in principle, the detector is filling the entire space. We just, the 3D picture basically takes out those sensors that didn't participate in the detection. All right, so let me give you an illustration of the top of the iceberg of the big data problem and how we established the evidence for the Higgs boson. So we basically collect a lot of data over 2011 and part of 2012, as you see there, different central mass energy. And what you see there is a bunch of data that is accumulated. So we don't know on an event by event basis if there is a Higgs boson, but we can tell after we have collected sufficient number of events as to whether there is a statistically strong evidence for a new particle. So what you see in red is basically particles that are in the standard model that are known and how they are produced. But you see in the area around 125, an accumulation of events, of data that is far away from the standard model without the Higgs boson. Okay, you see a tremendous excess of events that basically tells you that we have a new particle with a mass of 125 GeV, and then you model it according to the standard model prediction, and more or less it is consistent with the standard model prediction. You see there a new particle. This is using 4 leptons, but now you also have another channel, which is 2 photons, as I said earlier. So what you do is you basically collect a lot of 2 photon events. A lot of data is collected, and gradually an accumulation of events emerges in the same place. So when you model the background, you see a very strong deviation from a smooth background around 125, which is incompatible with a background-only hypothesis. So we basically exclude a background-only hypothesis with a very strong confidence level with 5 sigma or more. And by combining these 2 channels around the first half of 2012 and other channels, of course, we were able to establish unequivocal evidence, both ATLAS and CMS, 2 experiments independently, that a new particle has been discovered. Now, this is the tip of the iceberg, or what we call the big data problem, that I will introduce very soon. Before that, of course, comes the accolades. Obviously, there's people like us have spent at least a decade working on this and preparing for this, it was obviously for us an event of our lifetimes to basically discover a particle like that had been predicted basically 50 years prior. And as such, a Nobel Prize was awarded to the theorists, to 2 theorists. Unfortunately, one of them had passed years before in 2013. And you see there basically the team that led the discovery of that glass experiment. You can see me there without white hair there in the picture. And then after that, I transitioned to South Africa, and I remember talking to my very good friend Lucas Lebaba, who's a very well-known journalist in South Africa today, who interviewed me about, what's the use of the Higgs boson, and he felt that the connection to beer would be a very good way of illustrating it. I never confronted him on that, but I guess it is what it is. But today, what I'm going to be talking about is not just beer, but is technology transfer that emerges as a result of the discovery of the Higgs boson that brings particle physics to the forefront of technology transfer from fundamental science and fundamental research to a much broader context, which is what I will be talking about during the second half of my presentation. Before I do so, it's very important to remind everyone that the internet was in fact invented at CERN in the very early 90s. This was the work of computer scientists who worked with physicists to establish the first protocols for communications through emails, and that later led to the World Wide Web in order to exchange information. So it was particle physics because of the fact that we create a lot of data, and that data needs to be disseminated, that data needs to be exchanged, the analysis of that data needs to be communicated to people and scientists all over the world, that basically all these protocols, including protocols used for the World Wide Web and the internet in general, were created for the first time. And again, this is one of the best known spin-offs that CERN has given to the world in the broad sense of the word, one of its most famous technology transfer contributions to technology transfer by CERN. And in fact, the South African office, one of the South African offices, is in fact right across from this office where the internet was invented. Okay, so let me go into one of the most important aspects of particle physics and the Large Hadron Collider, which is the big data challenge. And that really drives a lot of the technology transfer that stems from the Large Hadron Collider, but not only. I will show a slide where the tech transfer is actually broader. So the challenge of particle physics is the following, that in order to go to smaller and smaller distances, in order to probe what's happening in the micro world of fundamental interactions, we have to collide particles more and more often. Okay, so just to give you a historical perspective, the LEP accelerator, which preceded the Large Hadron Collider, that is, I think it started taking data in 1989, collided particles every 22 microseconds. That was mind-boggling at the time. Remember, this is the 80s. And then new accelerators came in. There was another accelerator, the Tevatron in Chicago in the United States, where the time between collisions shrunk between 22 microseconds to 3.5 microseconds. Then came the Run 2, the upgrade of the Tevatron, where the time between collisions shrunk from 3.5 microseconds to 396 nanoseconds. We're now in the nanosecond range, okay, where essentially the accelerator collides with a frequency of 2.5 megahertz, okay, which is a huge number, 2.5 million times a second. So the Large Hadron Collider, in order to discover the Higgs boson, had to even further reduce the time between collisions to 25 nanoseconds. That's absolutely mind-boggling, and it's really an amazing technological advancement to be able to do such a thing. Essentially, the Large Hadron Collider collides clouds of protons 40 million times a second. So imagine the Large Hadron Collider provides data 40 million times every second, and the detectors have to record that data every second and all the time without gaps. And that's a tremendous challenge that leads to petabytes of data per second. So something really mind-boggling. And remember, the Large Hadron Collider was designed, or at least the concept was put forward already in the 80s, and the main technological methodologies and methods were already designed in the 90s. So imagine what kind of forward thinking you need to really achieve this problem. And this is really the mother of the big data problem. So essentially, the big data problem comes because we collide particles very, very often. In this particular case, 40 million times a second. So the detectors, which are massive constraints, which detect data with hundreds of millions of channels, they provide tremendous amount of data every second. And that basically leads to the generation of petabytes of data every second. Petabyte is a huge amount of data, but that happens every second. So detectors have to do a lot of real-time decisions. And from here emerges the epitome of the big data problem. And the fact of the matter is that the Higgs boson is produced very rarely. So you really have to create tremendous amounts, billions and billions of collisions to basically pick the one Higgs boson candidate, and do that many, many times so you have enough Higgs boson candidates to establish a evidence, okay? Because getting only one is not enough. And basically, this is resolved through a bunch of steps that the big data problem is composed of. So the detector creates about petabytes of data per second. There is a lot of processing online. 99% and 99.99% of the data is processed on the fly, real time. In fact, the big data problem is not just about computing. Computing sits at the very end of the big data problem. Most of the decisions are made in real time. That's not only true only for particle physics, but also for big data problems in general. And then the real-time decisions, which typically take microseconds to seconds, depending on what kind of accuracy you want to achieve, then you basically ship much smaller data sets to the computing model, something of the order of hundreds of megabytes per second. So you have to reduce petabytes per second down to gigabytes and megabytes. In this case, the computing technologies of today can handle rates of that order, hundreds of megabytes per second, and then you create a computing model. This is referred to as the worldwide LHC computing, or WLCG, that South Africa is a member of. And currently, or initially, was designed as a hierarchical system of computing farms and computing nodes all over the world, where it would be organized in terms of tiers. Tier 0 is CERN. They are basically surrounding it a bunch of tier 1 sites in the big countries, and then surrounding, you know, in this as a part of this mega distributed system of computing, tier 2 facilities, and South Africa has one at the CHPC. You can see here the picture as of 2017, basically about 167 sites in 42 countries. And you can see there in the Southern Hemisphere, Argentina, Brazil, Australia, and South Africa, as a part of this big data challenge. Big data is not just, and the internet and the big data is not the only tech transfer that CERN is known of. There's a huge list of accomplishments in technology transfer. A lot had to do with you know, medical physics and medical imaging and things like that, and also a lot of stuff related to electronics. CERN had to become extremely powerful in electronics, and as such, also in South Africa, we have electronics labs related to CERN, and there's a lot of tech transfer that has happened as a result of the fact that you need electronics to process these huge amounts of data. And you can see here examples of tech transfer activities in medical physics from techniques that were developed at CERN, coming from nuclear and particle physics. the PET, medical imaging, and also let's not forget that some cancers are treated with protons in facilities around the world. Okay, so let me move to the second half of my presentation. I think I'm more or less on time, is our contribution to COVID-19 and the post-COVID-19 world, and how particle physics and CERN are working together to provide broad impact and to further enhance technology transfer along the lines of the UN's SDG methodologies, and how we contribute to the SDG number 3. So in 2020, when the crisis became evident very, very quickly, around February or so, that South Africa, as anywhere else in the world, was going to face a pandemic, we were called in to help with the modeling of COVID-19. Why? Because you need to learn from the data. And we are basically a team of people that model on large amounts of data and use artificial intelligence to do so. So why us? Well, okay, you can see there a paper. I mean, when I was back in Wisconsin, we basically we introduced machine learning, artificial intelligence at the Large Hadron Collider back 20 years ago. So we've been doing machine learning in conjunction with a lot of data for quite some time. And I have to say, in the past 5 years or so, not just particle physics, but science in general has been adopting machine learning in a massive way, in a much more multidimensional way compared to how we used to use it, say, 20 years ago. 20 years ago, machine learning and AI was used for classification tasks, where you have a labeled problem and you want to separate signal of a new particle you want to find and the background, which is composed of particles you already know exist and you treat as backgrounds. These are classification techniques through supervised learning. But now the scope and the span of techniques and algorithms is just mind-boggling. It's been a complete explosion in the integration of much more sophisticated machine learning techniques into the data stream. And as such, there's a lot of a spin-off coming out of it into technology transfer through our activities at CERN. And okay, we are also victims of our own success, quote unquote, is that, you know, all our students, or most of them, end up basically being hired at top companies doing data science, and they don't stay in the field as such. So we have a problem with retention because the machine learning has become highly marketable these days. All right, so then our team was appointed in, I think, mid-2020 by the Premier of Gauteng to lead modeling efforts for Gauteng. So we're basically given through a memorandum of understanding and confidentiality agreements and all that, a lot of data that helped us understand the complexity of the problem. And they basically relied on us to use classical modeling techniques in epidemiology in conjunction with artificial intelligence. And I think that's what was novel at the time, is the implementation of machine learning into classical modeling to enhance classical modeling and bring it to a whole new level of understanding. In that machine learning, what machine learning does is to learn from the data, to model from the data, okay? If the system is very, very complex and you have almost no time to model it, artificial intelligence comes in to help you extract models from the data. And I have to say, it has been one of the most intense experiences in our lives, because our team was working 24/7. There was always somebody working at any point in time. And it was a very, very intense experience. We created, of course, a consortium that later included our collaborators in York, and then the Canadian IDRC provided a lot of funding that has been recently expanded quite a bit to think about how AI helps with the post-COVID-19 world. And I will talk about that at the very end. All right, so let me give you a few showcases of where artificial intelligence came in to enhance classical modeling in order to answer burning question. So if you remember, in the beginning of the pandemic was very much hotspot driven. So the task of government and policymakers at all levels and also on the ground was to identify where the pandemic was growing fastest, to identify hotspots and enact interventions that would help suppress the growth of those hotspots to stop it. So that was really one of the most important aspects of the management of the pandemic at the time. We're talking about 2020, and remember, back in those days, we had a very little understanding of what the implications to public health COVID-19 had, and we were basically learning as we went. And basically what happens here is that if you really want to use classical model, you need to have a tremendous amount of information that we didn't have at the time from the communities as to how each community and how the members of each community interact with each other to predict how these hotspots would evolve in time. So that clearly is that's a huge task, impossible task to do with basically no time, literally no time. I mean, remember, you're sitting in a committee, you have clinicians, epidemiologists, and then you have the office of the premier saying, look, what's happening, where are we going, how many beds do we need? You really have to give answers. So here, artificial intelligence, in particular brand of AI called unsupervised learning comes to help. In that unsupervised learning does not require a lot of pre-existing knowledge and generates clusters. And then we embed into those clusters classical techniques to model how those clusters will emerge and will evolve as a function of time, how the temporal evolution will look like. And artificial intelligence was absolutely critical in defining those clusters, those hotspots, and also in classifying them. We basically, together with IBM, we created a tool that allowed the population and policymakers understand where those hotspots are, how fast they're growing, and how dangerous they are. Okay. So our team did the artificial intelligence, IBM did the software. They were very good software engineers, and they developed a very fancy tool with which you could actually go down to the world and down to the street to really understand where the pandemic was. And as a matter of fact, we monitor social media. That was one of the things we did, as I will explain in a minute. And we actually were able to see that people were using the tool and say, aha, in our street there is a hotspot. And then people, tend to retract more. If they know there's a hotspot in their neighborhood, they tend to retract from social interaction. So this played also a role in containing. Typically during peak, we had about 200 to 300 hotspots in Hong. Let me move to another showcase of the use of AI. In 2020, the SANDF, the South African Defense Forces, were brought to the table. And you sit there with these generals, and they're, they're very practical and very smart. And they say, okay, when are waves going to take place? It's not a naive question, but it's the toughest question you can ask, because the reality and the fact of the matter is that classical models can't predict when a pandemic or when a wave is going to take off. And so the only thing you can do is to use artificial intelligence techniques to create and generate early detection algorithms. And you do that by training a particular type of machine learning algorithms on historical data. And then these algorithms give you the first signs, the first, so to say, red flags that the data is inconsistent with the absence of a wave. And it does it typically 2 months before the peak of the wave takes place. So you basically say, look, we cannot tell you when, but we can alert you with about 8 weeks in advance. So that was basically enough for them. I was also published. You can see there, you can see the methodologies used. I don't want to get into the nitty-gritty, but basically uses recurrent systems, recurrent neural networks that are nested in time, that learn from the past and predict the future. And then we basically created a website. This was an example for the third wave. And if the index basically was above the threshold for a few days in a row, you already could tell and could say that something is happening here and a wave is approaching, and then everybody gets alerted. And AI, what AI does is basically does it in a more efficient way, so it gives you an alert earlier. Okay, of course, this is not to say that classical techniques cannot do it, but AI will do it earlier, and a week or 2 weeks time frame is actually a lot in when it comes to management of the pandemic. So this was another showcase where AI was integrated into the modeling by giving an alert. Then came 2021, and remember, during the first half of 2021, we had a big problem of a scarcity of vaccines, okay? That changed quickly in 2022, in the second half of 2021, where vaccination hesitancy became the bigger problem. But initially, the problem was we didn't have enough jabs. So, of course, you have to first protect your frontline workers. That's clear, and that had to be done first. But once you have enough jabs to give to the population, is how do you administer it? And that's again a problem where artificial intelligence came in. As you remember, the rollout of the vaccines was phased. Phase 1 is frontline workers, and phase 2 some of the essential workers, but then populations, certain populations, and then comes phase 3 when you open up basically to the entire population. So it was phase 2 where AI had to come in to be able to provide answers as to what is the most efficient way to administer the vaccine so as to have maximum impact with a small number of vaccines. So that's a very well-defined problem, of optimization where data science come in and does things fairly comfortably. So we basically, I'm not gonna spend time here, but basically what we did is we were given data, especially hospital and mortality data from the Department of Health, and then using techniques that I referred to as weak supervision, we were able to create certain classifications of patients, and we basically were able to devise a smart algorithm that would drive, that would basically tell us what is the optimal path of delivery. And that's a typical problem of optimization, which we solve through weak supervision techniques. And basically what you do here, you create this smart algorithm. This graph gives you an illustration of the performance of the smart algorithm as to how you should phase it. Of course, you don't give a smart algorithm to policymakers. You basically give, the ages and the age ranges and the comorbidity ranges where the people that have to be administered the vaccine first, and the second class, the third class, and so on and so forth. So what you do is you basically turn a smooth algorithm into a discrete algorithm, which is what was implemented in the end. Because of course you cannot enact policy on the basis of a smart algorithm. You have to turn the smart algorithm into a binary, into classes of people that you administer the vaccine to first, and that's what was done. But underlying that policy was the smart algorithm, and you can see here in this graph on the x-axis is severe outcome, the fraction of people that have severe outcome, which is ICU or mortality, people that die or end up in ICU, and on the x-axis, on the horizontal axis, you have the fraction of the Houghton population. So if you follow this path, you basically, with about 20% of by vaccinating 20% of the population, you can have a reduction of a factor of basically 5 in the number of severe cases, ICUs and mortality. And that's really what actually happened. And you basically select certain classes of population to administer the jabs first. Now, the situation, tables turn very quickly around mid 2021, where the South African government was already getting a lot more vaccines. And then the problem became a different one, which was vaccination hesitancy, okay? And back in those days, back in those months, the government commissioned a survey that concluded that only 15%, 1.5, of the population was against taking the jab. So we thought, well, okay, this is going to be a walk in the park. Well, the reality sunk in, and we realized that vaccination hesitancy is a much more complex phenomenon than just anti-vaxxers, than just people that don't want to get vaccinated. And as soon as the numbers came and you look at the first derivatives, you say, this is absolutely inconsistent when you look from the modeling standpoint. And we were among the first to raise the alarm to policymakers that the pace at which the vaccines have been administered are absolutely inconsistent with the 15% vaccination hesitancy. That was absolutely evident, you could say, within the first month. And that means that we needed to go and hone in and trying to understand what the vaccination hesitancy was about. And we created another project with IBM, which pertained to the use of natural language processing. I forgot to add the publication. We have a couple of publications here as well with them, where we look at tweets and social media and start understanding with natural language processing, which is a branch of artificial intelligence that deals with strings, with texts. That's one of the most complicated machine learning algorithms you can build because of the complexity of language, things like sarcasm, things like ambiguous sentences, or ambiguous intentions, or covert criticism. Is a very complex phenomenon in natural language processing. So we really had to learn a lot, and IBM, I had to say, helped us a lot about how to process the data. So we basically established sentiment analysis of tweets. You can see here an example of how the hyperparameters optimization happened, the complexity, the mathematics that underlies the natural language processing to achieve the biggest possible efficiency of the understanding of the tweets. And we also created a dashboard for the different provinces of South Africa, the different types of sentiments. This was done by 2 members of our team. And you can really see where the negativity, the positivity is actually located here, especially through the sentiment analysis of tweets. So let me move on to now the post-COVID-19. One of the things we're trying to do in a much more, so to say, systematic way, now that we have more time, is to include all possible sources of data to prevent, or not just to prevent, to alert, create early detection algorithms of new pandemics. And one of the big gaps in data collection that we had during COVID, because of lack of time, was satellite data. And satellite data, which is actually available for free from the European Space Agency and also partly by NASA, that covers the entire African continent, provides a tremendous amount of information about pandemic outbreak. And this is now basically moving away from COVID-19 into the post-COVID-19 public health problem, and the use of AI in a much more sophisticated way, in a much more multidimensional way. So you can see when one of the showcases we're looking into is malaria as a showcase. Malaria is not a big problem in South Africa, so we're using more data from Ghana and Kenya. But nonetheless, it's important to really correlate the outbreak of malaria as a showcase of disease with factors on the ground that can be monitored with satellite data. There's been already in the field of malaria, there's been quite some studies already, but never using artificial intelligence. So there's been papers. This is a graph from a paper from 2020 or 2021, where there's a look, this is all the satellite data that is relevant to the malaria problem, in particular the mosquito habitats. And if you were to combine all this data, you would get a better understanding of how the pandemic would evolve, or you could predict outbreaks. And the good news is that we came in and said, okay, now we can do artificial intelligence, we can do machine learning, because machine learning is extremely good at combining very large amounts of high dimensional data to create models. And we basically have learned already over this past few months and years to extract information from the satellite data, look at all the indexes created by the satellite. The satellites themselves, they emit electromagnetic waves with particular polarizations, and the way they are reflected on the ground give information about vegetation, humidities, which are relevant to the mosquito habitat. And I'm going to move to the last topic now with the minutes that are left, which brings us to a fairly large project that the WHO has been screaming about, where again, CERN is becoming a very important stakeholder to provide answers to. And one of the biggest gaps, we have satellite data, so that's not really a gap, it's just that we haven't used it. So now it's been integrated. But one of the biggest gaps in public health is air quality. And the more you talk to experts in global health, the more you realize how important air quality is, both air quality and quality of water. Okay, and the problem that we have, not just in the global south, but in the global north, is the dismal collection of air quality monitoring and the air quality that we have worldwide. Of course, more acutely, the problem is more acute, of course, in the global south. And the fact of the matter is that air quality is related to a huge array of conditions, many, many deaths worldwide, and is strongly connected with vulnerability. So we've launched an international project with people in Europe, North America, and Africa, which is funded by the Canadian IDRC, also with the support of the DSI, NRF, and the SSM program, and very importantly, CERN. And I will finish my presentation. I started my presentation with CERN. I will close my presentation with CERN. And this is some nice graphs on the brochures, as we are also fundraising with foundations. And basically the future of pandemic detection is really artificial intelligence. The collection of a lot of data, satellite, clinical, climate, epidemiological, WHO, CDC, water, air, social media, citizen science, into a massive artificial intelligence algorithm that would help us alert WHO governments as to the emergence of new pandemics early on. And is the integration of these data sets and the modeling stems from artificial intelligence. So and actually, I should also mention that particle physics is going in exactly the same direction, in the direction of enhancing dimensionality and enhancing complexity. We have entered in the past few years in particle physics into the era of deep learning with a huge amount of variables, a huge amount of indexes. This is exactly the same direction as well. So we're sort of going in parallel here. Air is a huge problem. I don't think I need to, I'm probably preaching to the choir, but it's actually, yesterday I was actually talking to some experts in Netcare. They even gave me even more showcases. They're telling me the problem of asthma in South Africa has been absolutely huge. I was talking to a lady, a French lady, a very well-known person. She was a student of the doctor that isolated the HIV virus, who was a co-recipient of the Nobel Prize in medicine, and she moved to South Africa and opened a HIV clinic in Soweto, and she is an enthusiast of how important is the measurement of the quality of air, and how many conditions emerge in South Africa because of poor quality of air. So that was very enlightening and very nice to see. We created a consortium that includes about 20 odd stakeholders globally, including some industries that are giving us in-kind contributions. We have a website that's now been enhanced. I hope the slides will be available to the community so people can look into this website and how it's growing and how fundraising works and things like that. And we also inform the community about the progress that has been taking place with the use of artificial intelligence and sensors, which is our core competency in particle physics. This is an example of one of the proof of concept projects. The project is composed of developing open source low cost sensors. One of the biggest stumbling hurdles that the world has and the global south has is the cost of sensors. There's a lot of business models underlying them, and the sensors are way too expensive. They're hundreds of dollars. But the fact of the matter is that the basic components that are available in the market are much cheaper than that. So what we want to do, and what we are doing already, this is a proof of principle, is that you can combine low-cost technologies into a low-cost device under $50, and that will enhance the ability of governments to roll out these sensors in a much wider space. You have here on the right a Japanese, one of the best sensors of particulate matter, 2.5 microns in the world, which is a low-cost device together with Nordic Semiconductor. This is not a Norwegian company that develops low-cost chips for communications, which is essential to IoT devices. And this is done in collaboration with CERN, may I add. And I will close in a couple of minutes. So the laboratory CERN, as I said, I started with CERN, I end with CERN. We are now about to finalize the agreement for this project to be hosted at the CERN Green Village, which is an initiative of CERN to demonstrate that the particle physics has very broad impact, but it's also very green. And this is the first project of the CERN Green Village, our project, the air quality project, that has become the flagship project and the first project of the CERN Green Village. And then the idea is the following. You see here a Google map of CERN. CERN is this small triangle here, because the area, believe it or not, is underdeveloped in terms of infrastructure. There's very few roads that link France with Switzerland. This is one of the nodes here. CERN is right next to a node, next to a border passage of France and Switzerland. There's a tremendous amount of pollution here. And CERN is, of course, very concerned about it. The cost of monitoring is very high. Even CERN has problems with it. And they are allowing us to deploy this low-cost system in order to detect highly polluted areas. Of course, low cost doesn't mean that it's very accurate, but it's accurate enough to establish poor quality. So low cost sensors are good enough to say that the quality of air is significantly worse or worse than the WHO standard. So we can establish poor quality of air. We can't really establish good quality, but what we really want is to establish poor quality. And with this, I want to close my presentation, and again thank the organizers for giving me the chance to address the audience. Thank you very much.